What's up, everybody? It's Mr. Hutch here, and this is your probability study guide. You can see how it's organized by lessons here. We're going to go through and let you check your work. Examples are on the left, practices on the right. Using Luke's 10-sided solid, describe an event that is certain and one that's impossible. I'm going to write it in that probability notation, which is what you're going to need to do for your test. So based on his solid, which is here, look at that nice line. He has a 10-sided solid, which they just mean a dice. So an event that is certain would be the probability of rolling a 1 through 10. I can guarantee that's going to happen. Okay, something, a 1, 2, 3, 4, 5, 6, 7, 8, or 9, or 10. So this is my certain situation. And my impossible would be the probability of rolling an 11. It's just not possible with a 10-sided die. So this is impossible. All right, number 2, spinner with 8 equal size sections is used for a game. Based on the description below, is the spinner a fair spinner? Okay, so the probability the pointer will land on a yellow is 1 out of 4. So one thing that'll help me is to sort of draw this out. So here's my 4, 5, 6, 7, 8. So the probability that it will land on a yellow is 1 out of 4. So that means this is yellow, this is yellow. Probability the pointer will land on a blue is 2 out of 8. So here's blue and blue. Probabilities that the pointer will land on a green or a red are both 25%. So that means green and red, because 25% is 1/4 of the circle. So based on all that information, is the spinner fair? Yes, because there are all equal, how about we spell equal right? Equal probabilities, okay? And so there we go. But you can see how the picture really helps solve that. Your test question is number 1. So you're going to have to identify, you're going to have to write something like this and something like this, just so you know. All right, lesson 9-2. This is about understanding theoretical probability. Remember, theoretical is what should happen. So using the example, 15 people take out a slip of paper from a bucket without looking. They record their results before placing the slip back in. How many times is a slip labeled 5 expected to be drawn? So we're looking down at this information here. There's numbers 1 through 5. The probability of getting a 1 or a 2 or a 3 or a 4 or 5 is 1 out of 5. Okay, so they already list that theoretical probability. And so we're wondering, what about the probability of getting a 5? Well, that probability is 1 out of 5. Okay, we could also represent it like this. The probability of getting a 5 equals 1/5. And so then our question is, what about 15 people? So remember, our trick for this is remembering predicting probability, you make a proportion. And so we're wondering, well, rather than that single probability, what about if I have 15 people instead? What's my x going to be? I can see that my proportion is just going to be times 3 over 3. And so my prediction of how many times a slip labeled 5 would be expected to be drawn would be 3 times. Okay, so you will have to do a problem like this on your test. So make sure you understand that process and what that needs to look like. All right, lesson 9-3, understanding experimental probability. Experimental probability is just running an experiment. So it's different than theoretical. Because theoretical is what should happen. Experimental has some randomness to it. Okay, but remember, the more experimental you do, the closer it gets to that theoretical probability. So we have Jalen, maybe, and Paula spin the pointer 30 times. So that's good information to know, and get the results shown in the table, which is here. Okay, so obviously if I add all those up, they're going to add up to 30. What is the theoretical probability of the pointer landing on a number 2? So theoretical, meaning what should happen. Well, there's only 1, 2. So the probability of landing on a 2, if I'm using this probability for notation here, is 1/4 or 25%. Based on the results of the table, how does the experimental probability of the pointer landing on 2 compare? So here's my data of Jalen and Paula landing on a 2. I'm going to add those up. Okay, so we have our 8 plus 5, 8 plus 5 is 13. And so we have 13 out of, and remember how many times did they go? That was up top, 13 out of 30 times. It landed on a 2. Okay, and so that's our theoretical probability. Let's go ahead and divide those up so that we can compare. So let's grab the calculator out here. 13 divided by 30 is 0.43. 0.3, oops, sorry, not 0.3. Boop, 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 boop. 0.43 with the 3 repeating, or swoop if I'm looking at a percentage, and I have 43.3 repeating percent, okay, chance, whereas my probability up above is 0.25 or 25% chance. So the question is, how does the experimental probability compare to the theoretical? You need an actual sentence, and on the test, you're going to need a comparison sentence. So I'm going to say the experimental probability is greater than, okay, so when we're comparing, we use greater than or less than, the theoretical, okay? And if you want to be more specific, you could even say exactly how much greater than, or you could say about how much greater than is an option as well, okay? And it would help if you spelled experimental correctly with an E. All right, next one, number 2. Based on the results in the table, about how many times should Jalen and Paula expect the pointer to land on a 4 out of the total 130, out of a total 130 spins? So let's go ahead and first of all, notice it says based on the results of the table. So they don't want you to use the theoretical, they want you to use their experimental data. So now let's go ahead and take a look at the 4 out of 130. So we'll look at that in blue. So if I'm looking up above, that's this right here. So 7 plus 10 is 17. And so we're looking at 17. Remember, the experimental is out of 30. And when we want to predict a larger amount, predicting means probability makes a proportion. So set it equal to what you're trying to check out. And so we want it to be out of 130 instead. And we're going to solve for x. So we have a couple ways to solve this. Remember, we can do means extremes, or we can check and see if we can identify the multiplier. So let's go ahead and do that first, because if that works, it is nice and easy. we get a repeating decimal, so we can't be doing it that way. So I'm going to have to do means extremes for this one. So let's go ahead and we have 30x equals 130 times 17, 2,210, divide by 30, and we get x equals 73.6 repeating. Okay, and so let's look at our information. It says, about how many times should Jalen and Paula expect the pointer to land on 4 out of a total 130 spins? So they can expect about 74 times. Okay. So because it's an about, maybe you could have used the multiplier. Let's go ahead and see what that would have looked like. 130 divided by 30. There's the multiplier times 17. 73.6 repeating. Yeah, so you end up getting the same thing since it said about. Okay. So that'll be good with that. You're not going to have to explain your answer on your test. As long as you show your work, you're going to be good with that one. Okay. All right, let's go ahead and move to your next lesson chunk, which is 9-4. This is using probability models. A probability model, remember, has a sample space and lists the events and their probabilities, okay? And so you have to have both of those on the test. I break it down for you. You just have to remember what a sample space is and how to properly list the probabilities using that probability notation. So for the practice, it says Abe has a different spinner. He also wants to develop a probability model. How would his probability model be the same as, and how will it be different from Jenna's model? So here's Jenna's model over here. Okay, you can see the sample space looks like this. S equals, and then they list out the information. You can even do abbreviations to show the sample space. And then they list the events and their probabilities. So this is what you have to do when you do yours for your test. They are asking you in this one, though, how would Abe's spinner look different? Here's a little secret for you on the test. I actually have Abe's spinner on there. So if you practice writing the sample space on here of Abe's spinner and listing the probabilities, that's exactly what you'll have to do for the test. Hint, hint. All right, so how is his sample space going to be different? Well, obviously, his sample space is just going to have blue, 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 white, 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 whereas Jenna's has blue and red and yellow, and then 3 whites. Okay, so that's one way that the model is going to be different. It's going to be the same because it has, look, we have 6, 6 spaces there, and we have 6 spaces in the other, so that's one way it's the same. You're not going to have to compare spinners on your test, so I'm not too worried about that right now, but it is good to talk about it and look at it. All right, now let's think about how the probabilities are going to be different. Well, obviously you have a better chance of landing on a blue, but you do have the same exact chance of landing on a white. So these are all the same things that are similar and different, but keep in mind, again, remember you're going to have to do this for the test, okay? So let's go ahead and practice that with the one down here. Here's a totally different spinner. It says, what is the probability that a pointer will land on a color that is not red? Well, out of 6, there's the probability of not red, this is using correct probability notation that I expect you to do, is 5 out of 6, continue your equal sign, or 83%, 0.3 repeating percent. Okay, so you need to represent it like that. What's the sample space? This is what you're going to have to do on your test. So we write S equals, and we do this little bracket like that, okay? And then we list the colors. So we have blue, comma, and then I'm going to go with orange, comma, yellow, comma, white, comma, red. And then close out the brackets. So that's sample space. I'm going to highlight it because that's what you're going to have to do on your test, okay? And then you also have to list the probabilities of each one. So I'm going to go ahead and show you what I mean by that. You would then have to say the probability of red equals 1/6 and list the percentage. Probability of white equals 2/6 and list the percentage. Probability of blue equals 1/6, list the percentage. Probability of orange, I know it's a little bit annoying, but just do it anyway. And probability of yellow equals, at least a lot of them are repetitive. So once you know what 1/6 is, you can just repeat that. So swoop, 16.6 repeating. And you can copy that. So I'm just showing you this because you are going to have to do this for your test, is the sample space and the list of probabilities, and that's a probability model. Okay, 2/6 is 0.3 repeating, so 33.3 repeating percent. Okay, so this along with the sample space is what you'll need to do. Okay. All right, number 4, Walter will spin the pointer 50 times. About how many times will the pointer land on each color? So what you're going to do is, since you know the base ratio for each color, the probability of landing on a red is 1/6. And so here's our 1/6. Set it equal. We're predicting if we did 50 times, what would the amount of times it lands be. So let's check the multiplier. 50 divided by 6, 8.3 repeating. And so because that's a multiplier and it's actually going to be times 1 in the numerator, that's actually the answer in the top. So 8.3 repeating. Because it also does say about. And so we can say red is about 8 times. And that's going to be the same for blue, orange, and yellow. Okay, are the same. Let's just go like this to save time. And then white is going to be a little bit different because white is 2/6. We can go ahead and reduce that to make our math work a little bit easier. Let's just see how it plays out, keeping it as it is. 50 divided by 6 times 2. Since we're doing about, this is okay to do it this way. 16.6 repeating. And so we have the white would be expected about 17 times. Okay, so there's some good practice on making predictions with larger amounts based on that probability model. Okay, all right, let's go ahead to 9-5, determining outcomes of compound events. The basics of this just means how many outcomes are there. This is the probability of that outcome. Okay, so that's the difference between the two. So here we go with number 1. A basket contains a red, a yellow, and a green apple. The second basket contains an orange, a lemon, and a peach. They want you to make a list to show all the outcomes in the sample space. Remember, the lists are very risky, so you'd have to be very, very, very careful with this. So we have to stay very organized. So we have a red, And the second option then is orange, lemon, or peach. So I have red, orange, red, lemon, red, peach. And then I'm going to move to my next one, yellow, orange, yellow, lemon, yellow, peach. Then move to the next one, green, orange, green, lemon, green, peach. You just have to be very, very careful. You can see why a table or tree diagram would be a safer choice. Either way, we showed all the possible outcomes. We also know the trick of just doing 3 times 3 equals 9 outcomes. Okay. All right, number 2, Simon is playing a game with letter tiles. He has 5 tiles remaining and will spell a new word by placing 2 tiles, first a consonant, then a vowel, in front of a Y already on the board. Complete the table below to describe all the combinations of tiles that Simon can use to spell a new word. And so we have a B and an A, like this. We have a B and an O. We have an S and an A, an S and an O, a J and an A, a J and an O. Okay. And so let's reread and see what the question is. He has 5 tiles remaining and will spell a new word by placing 2 tiles, first a consonant, then a vowel, in front of a Y that's already on the board. Describe all the combinations that Simon can use to spell a new word. So this one's a little bit tricky. Obviously, there's 6 possible combinations, but there's this Y that exists in the story problem. Okay. And it turns out that they all do make a word, so we are using all those possible combinations. I wanted to do that to just make sure they weren't tricking us with a word that didn't exist. So we've completed the table. There's 6 options. Again, we have 3 times 2 equals 6. So we already knew that to be true anyway. All right, lesson 9-6. Okay, we just have 2 more. Find the probability of compound events. Remember with compound events, the trick with this was the probability of A times the probability of B tells us our total outcomes. That's as long as we're replacing things so that B still has the same denominator. If we're not replacing, we know it's probability of A times the probability of B minus that one denominator. Okay. All right, so let's go ahead and take a look. We have one set of cards has a beach, a road, a desert, a mountain, and an island. So 1, 2, 3, 4, 5. And then the second set of cards has car, truck, and van. Complete the table and find the probability of randomly drawing a mountain card and a truck card. Okay, so we have 2 ways of doing this. The mathematical way up above here is just finding the probability of drawing a mountain card and then a truck card. Anytime we're doing one, then the other, we know you can just do probability of the one times the probability of the other. So mathematically, probability of drawing a mountain card is 1 out of 1, 2, 3, 4, 5. Probability of drawing a truck card is 1 out of 3. The mathematical trick with this is we know we can do 1/5 times 1/3, and we get 1/15. Okay, and so there's our answer already, but they are telling us to complete the table. So I don't care about any of the other stuff. I just want to know probability of drawing a mountain card and a truck card. So I have mountain and truck like that, and that's how we would represent those. There's only one of those that are going to exist, and it is out of the 15, and so you can see it creates 1/15. Okay, just like the math that we did already. All right, let's go ahead and move on to the next problem here. And by the way, you either can just do the math trick with that, or you can create a table or a tree diagram to actually calculate it or look to figure it out instead. It's going to be up to you on the test. All right, this one we did one day, and so you're really going to want to pay attention to this because we also did it in a more virtual setting also. His favorite cereals include one of 3 prizes inside each box. The chance of getting each prize is equally likely. Felix conducts a simulation to see what his chances are of collecting all 3 prizes if he buys 5 boxes over time. Each section represents a possible prize. Okay, so these are called simulations, remember, because we're not actually pulling out of a box to do experimental probability. We're using a spinner or dice or something like that to simulate it, or a coin or something like that. Okay, and so what you can see, he tested pretending we have like box 1, box 2, and so on. So he pretended that there's 5 boxes and spun the spinner and collected data. So this is like a trial of reaching in 5 boxes and seeing what he would get. Okay, and so when we look at this, we can see his trial spun a yellow, then a green, green, blue, blue. Okay, which represent different prizes. The question is, based on the simulation, what is the probability that he'll collect all 3 prizes when he just buys 5 boxes? Okay, and so we're looking at each trial, okay, each like sort of trial set here, and go, okay, in his set, his little trial set here of 5 boxes, did he get all 3 prizes? Well, yes, he did. So I'm going to start circling. No, he didn't. Yes, he did. Yes, he did. He got all 3. He got all 3. No, he didn't. And yes, he did. Okay. So we're looking at how many did he collect all 3 prizes? Well, 1, 2, 3, 4, 5, 6 out of 8. Okay. So it's a 6 out of 8 probability of him collecting all 3 prizes. Let's go ahead and show the percentage, which equals 75%. And if I'm writing it with that probability notation, it would look like this. Probability, all 3 prizes. Okay. And that would be my answer. You are going to have to identify the probability. One very similar to number 2, wink, wink. Reese is playing a carnival game in which he must guess under which 2 cups a ball is hidden. So he did this simulation with a coin, since it's equally likely, one has a ball under it and one doesn't. So he used a coin to simulate this situation. And so we're wondering, what's the probability that Reese will win at least 2 of his next 4 games? So understand, though, this is a game, a game, a game, and a game. So we're just predicting the next 4 games, okay, based on what we see. So what are we circling? That's what you're focusing on. We're going to circle ones where he won at least 2 within that set, okay? So he winning is heads, so he won at least 2. He didn't win 2, didn't. He did win 2, he didn't. He did win 2, he did, he did, he did, and he did. Okay, so we have 1, 2, 3, 4, 5, 6, 7 out of 10. So our probability is 7 out of 10 that he would win at least 2. And so that is what we say. And so 7 divided by 10 is obviously 7/10, which equals swoop, swoop, 70% chance, okay, of winning at least 2 on his next games. And again, probability notation, I would say the probability of getting at least 2 wins. Okay. And that is it. Okay. So this is, pay close attention to this one here. This is what you're going to have to do for your test. All right, that is your study guide. Really make sure you understand those. You can look at the examples on the side if you need more. Go back through our homeworks or things like that for extra practice.